Regularization techniques in machine learning. In machine learning, building a model that performs well on training data is relatively easy. The real challenge is making sure that the model also performs well on new, unseen data. When a model performs very well on training data but poorly on new data, this problem is called overfitting. Overfitting happens when the model learns not only the actual patterns in the data but also the noise and random fluctuations. As a result, the model becomes too specific to the training data and fails to generalize. To solve this problem, we use something called regularization. Regularization techniques help control the complexity of the model and make it more generalizable. Let's start with one of the most important techniques, L1 regularization. L1 regularization works by adding a penalty to the model for having large weights. It pushes some of the feature weights to exactly 0. This means the model automatically removes less important features. You can think of L1 like a sculptor carving a statue. The sculptor removes unnecessary parts and keeps only what is important. Similarly, L1 keeps only the most useful features and removes the rest. This makes the model simpler and easier to understand. Next is L2 regularization. L2 regularization also adds a penalty for large weights, but instead of removing features completely, it reduces their impact. It makes sure that no single feature becomes too dominant. Imagine balancing weights on a scale. L2 makes sure that all weights are distributed evenly, so the model becomes stable and smooth. It does not eliminate features, but it controls their influence. Now let's talk about dropout, which is mainly used in neural networks. Dropout works in a very interesting way. During training, it randomly turns off some neurons in the network. This means the model cannot rely too much on any single neuron. Think of it like a team where some players randomly sit out during practice. The rest of the team has to adapt and perform without depending on one player. This makes the whole team stronger and more flexible. Dropout helps the model learn multiple patterns instead of memorizing one path, which improves generalization. Another important technique is early stopping. Early stopping means we stop training the model when its performance on validation data stops improving. If we continue training for too long, the model starts overfitting. It's like studying for an exam. Studying too little is bad, but studying too much without rest can also reduce performance. Early stopping finds the perfect balance. Now let's understand data augmentation. Data augmentation increases the size and diversity of the dataset without collecting new data. For example, in image data, we can rotate, flip, or crop images. This forces the model to learn general patterns instead of memorizing exact examples. It's like practicing with different versions of the same problem. Another technique is batch normalization. Batch normalization normalizes the data flowing through the network. It makes training faster and more stable. At the same time, it introduces a small amount of noise, which helps prevent overfitting. Feature selection is also a form of regularization. Instead of using all features, we only select the most important ones. This reduces complexity and improves model performance. Sometimes this is done using domain knowledge or statistical methods. Ensemble methods are also useful. In ensemble learning, we combine multiple models to make predictions. Techniques like bagging and boosting help reduce errors. The idea is simple: when multiple models work together, their mistakes cancel out, leading to better results. Another interesting method is noise injection. In this method, we add small random noise to inputs or weights during training. This prevents the model from memorizing exact patterns and forces it to learn more general features. Weight sharing is commonly used in convolutional neural networks. Instead of learning separate weights for every position, the model shares weights across different parts of the input. This reduces the number of parameters and improves generalization. Max norm constraints are another technique where we limit how large the weights can grow. This prevents any neuron from becoming too powerful. Label smoothing is used in classification problems. Instead of assigning full probability to the correct class, we slightly distribute the probability among other classes. This prevents the model from becoming overconfident. Adversarial training is an advanced technique. Here, we intentionally modify inputs slightly to confuse the model and then train the model on these difficult examples. This makes the model more robust. Sometimes, the best regularization is simply making the model simpler. Using fewer layers, fewer neurons, or simpler algorithms can naturally reduce overfitting. Simpler models are often more reliable and easier to understand. Another advanced method is knowledge distillation. In this approach, a smaller model learns from a larger, well-trained model. The smaller model captures important patterns without overfitting. Gradient clipping is also useful, especially in deep learning. It prevents extremely large updates to the model, ensuring stable training and reducing overfitting. There are also techniques like mix-up and cut-mix. These methods combine different data samples to create new training examples. This helps the model learn more generalized patterns. Finally, let's understand why regularization is so important. Real-world data is messy, noisy, and incomplete. Without regularization, models tend to memorize data instead of learning patterns. Regularization helps, it reduces overfitting, it improves generalization, makes models more stable, it helps in better decision making. In simple words, regularization teaches the model to focus on what truly matters and ignore unnecessary details. To conclude, techniques like L1, L2, dropout, early stopping, and data augmentation are essential tools in machine learning. They ensure that models not only perform well on training data but also deliver reliable results in real-world scenarios. And that is why regularization is a key concept in building strong, efficient, and trustworthy machine learning models.